Good morning, everyone, and welcome to today's event. Regretfully, we have to start today's proceedings on a somber note. As you're aware, Professor R. Kumar of the Indian Institute of Science passed away at the age of 87 a few days ago on the 7th of this month. During his illustrious career, he was a gigantic presence on the country's engineering scene. As a preeminent chemical engineer, institution builder, professional, and a warm human being, Professor Kumar has touched many lives during his long career, and we thought it appropriate to pay homage to this great son of India before we go ahead with the scheduled events of the day. Professor Kumar was born in Punjab in 1934 and was educated in Punjab and Delhi universities. He joined the Indian Institute of Science, then known as the Tata Institute, in 1958 and remained associated with the institute in various capacities for 64 years till his passing. After his superannuation in 1995, he continued his association with the Chemical Engineering Department at IISc and was also an honorary professor at JNCASR. A brilliant chemical engineer, Professor Kumar was among the pioneering contributors to an analytical approach to chemical engineering problems in India. His various contributions on multi-phase phenomena, in particular bubble and drop phenomena, sonochemistry, foam beds, to mention a few of the many themes he investigated, are well cited and have inspired large tracts of research in those areas. A feature of his approach in research was a keen awareness of the practical angle, even as he dwelt in esoteric theoretical concepts. His contributions to what has come to be known as appropriate technology are well documented. He was one of the most highly decorated chemical engineers in the country, with the S.S. Bhatnagar Award from CSIR, the Vasvik Award, the Om Prakash Bhasin Award, the Shanti Swarup Bhatnagar Medal of INSA, to mention a few. He was a fellow of the Indian National Science Academy, Indian Academy of Sciences, and the Indian National Academy of Engineering. For his multifarious contributions to the profession and the nation, the Government of India awarded him the Padma Bhushan in 2003. Professor Kumar's contributions to the engineering profession have been equally stellar. A large part of the credit for building up the chemical engineering department at IISc to the status it occupies today as one of the foremost centers of research and learning in the country goes to him. His contributions on various government bodies and boards have been very significant. He served IISc in various administrative capacities and also served on the governing body of the CSIR. Above all, Professor Kumar was a very warm human being, always jovial and friendly. He was a great nurturer of young talent. His direct students, as well as a much larger body of students he touched directly or indirectly, have themselves gone on to make very significant contributions to the engineering profession and the country. As a mark of respect to the departed soul, may I now request all of you to stand in silence for a minute. Thank you. We will now start the scheduled event, and I will request Rahul to please share the introductory slides. Yeah. Sorry about the short delay in beginning today's event. There were some technical issues that we were trying to sort out. Can you go to the slide on the speaker? So we have the pleasure of having Professor Chandra Venkataraman of IIT Bombay address us today on the theme of Why is Urban Air Pollution a Regional Misnomer? The India Narrative. Professor Venkataraman is the Shobha Dikshit Chair Professor in the Interdisciplinary Program in Climate Studies and the Department of Chemical Engineering at IIT Bombay. Her research focuses on the intersection of technology and emissions, aerosol science and engineering, and environmental sustainability policy. She has worked widely on air pollution, climate change, and nanoparticle aerosol drug delivery. Professor Venkataraman was the founding convener of the Interdisciplinary Program in Climate Studies, a first such doctoral program in India. She is the national coordinator of the 22 institution network called as Coalesce. This network has been established by the MOE FCC, and it works towards understanding the regional carbonaceous aerosol life cycle, climate impacts, and climate feedback to air quality. She has mentored women STEM faculty and worked to address institutional systems that could support their advancement. Professor Venkataraman's research has contributed over 100 journal publications, including publications in Science and so on, a book, and 4 patents. She has a committed research mentor. She is a committed research mentor with former students in academia and R&D positions the world over. She has been recognized through a Fulbright Nehru Fellowship in 2012, the PRL Vikram Sarabhai and IGPP START Awards, a citation database listing among top 2% Indian scientists in atmospheric and climate science, and she's been elected to all the academies of India, Scientific and Engineering Academies of India, INAE, NASI, IASC, and INSA. With that, I will hand over the session to Professor Chandra Venkataraman, and before she begins, let me make an announcement about a housekeeping kind of announcement. All the audience will remain muted throughout the talk. Any questions you have, please indicate in the Q&A box or on the chat box. At the end of the session, I will pose those questions to Professor Chandra, and she will reply to them. Chandra, over to you.
Thank you, Suresh, for the introduction, and which is a very kind introduction. Thank you to colleagues in INAE for this opportunity to talk about an important pressing problem, air pollution in India, which we're hearing, of course, day after day in the media in terms of alarming levels. So urban air pollution is a term that we have imported from the developed countries. And so the question is, does it apply here? And if not, then why not? It's not moving. Coming to the fact that we want to understand what is the disease that is caused by multiple risk factors. There is this project called the Global Burden of Disease, about 2,500 scientists worldwide. And what we're seeing here is a large number of risk factors: high blood pressure, diabetes, smoking, cholesterol, etc. But third on that list is exposure to ambient air pollution and particulate air pollution. So the particles we are breathing in, pollution particles. The fourth one is household air pollution, which arises from exposure to solid fuels like biomass, chulas, coal, etc., etc. Now, how does this manifest itself? If we look at, for example, the dark blue, then that is chronic respiratory diseases. The light blue is cardiovascular diseases, and the orange is lower respiratory infection. So between the dark blue and orange, about half of it from respiratory diseases and half of it from cardiovascular diseases, which are being worsened. So if we have ambient particulate pollution contributing to about 10 lakhs excess premature deaths, we'll talk about how this is estimated, etc. So in this context, we have a national clean air program and that aims to cut PM 2.5 by 20 to 30% by 2024 over 2017 levels. And the thing is that it has been launched with a very strong city focus and with the idea that we will have city action plans in over 200 cities. So then, we use different frameworks to study air pollution. One of them is called the Top-Down Framework, which I won't talk about today, where you start with large databases of measurements, and then you go on to, inverting them in matrix operations to identify factors or sources. I guess what I should start by saying is, if we just measure pollution levels, we don't know where it is coming from. And when we don't know where it is coming from, which source is contributing it, we don't know what to control. So really what we need to do is identify what are the sources that are contributing to air pollution. And so the method that I will talk about today is what is called a bottom-up method, where we're really looking at developing databases of emissions, deploying them in what are called air pollution models over here, estimating through simulations what is the amount from each source, and then population impacts. So the questions we're trying to answer are, is it really an urban problem, and what is the scale at which we should try to address it? So quickly taking a look at emissions modeling, this platform called Smog India, speciated multi-pollutant generator, which we are calling Smog, has been developed over more than a decade in my group. And this slide is basically saying that you need to have a lot of input data, a large number of amount of primary data, maybe secondary data, and have a way to have a emission management system to then be able to calculate spatially and temporally result. So we currently have about 25 kilometer by 25 kilometer all over India, but we are trying to go to 5 kilometer resolution, and we are able to do monthly mean, which then can be broken down to daily further. And so this gives us baseline emissions, the cartoon shown at the top, and then we can also then say future scenarios. What happens to these emissions if we do nothing? The top line, if we do what we can, middle line, but if we really decide that we want to solve the problem and reduce it. And then we make these assessments through the models. As we're engineers here, we all like to make sure that the underpinning math is actually working, etc. So there are these methodologies for calculating emissions, and so therefore we have to go through the whole gamut of sectors: industry, residential, agriculture, informal and informal industry. So informal industry provides the largest part of employment in our country, and that includes food and agro processing, whether we're talking about making koya, poha, drying spices, drying food grains, making tea, coffee, and in fact even commercial cooking like in restaurants and so on. A lot of this is driven by biomass use, maybe technologies of combustion which are not very clean, and so on. Then we have waste burning, and we also know that our residential sector is characterized by a lot of our citizens needing to rely on chulas burning biomass fuels. So while we say simply that we have a multiple set of pollutants, which is particulate matter, a bunch of gases, etc., there's a set of sectors, S, and we say that we have which is fuel consumption, and then we have a fuel type. But then we don't just restrict ourselves to fuel type. We, go beyond that and say if I burn coal in a pulverized coal combustion boiler, then I get different emissions from if I burn it in a sigri, or if I burn it in a stoker, or and so on. So with all of these kinds of things, very, very data intensive activity, we can calculate emissions. In cases like, we say activity rates and production, this can get complicated. For example, if you're talking about on-road transport, the activity A needs to say what are the on-road vehicles. So we cannot just use sales data. We have to have some kind of a survival fraction of vehicles sold in different years, and then say how much each of these types of vehicles, how much mean vehicle kilometers traveled, and then of course the emission factors. And then, there are different ways of propagating uncertainty through them. So with this idea, we've built this inventory, which is underpinned, and what is being shown here is that 22 institution project, where nationwide surveys were done, particularly related to residential, agricultural residue burning, fired clay brick production, all of these sources which are not very well understood. And what this is basically saying is, we've done over 20,000 surveys in these lesser known sectors, while we address all the other sectors, formal, informal industry. So, all, whether it's thermal power, cement, whether it's all the petrochemicals, everything, all of them are in there. And then we go ahead and resolve it into a spatial database or map of emissions, as you would. And this is just saying that, we need to have primary data, secondary data, measurements, spatial proxies to distribute it correctly, and have a framework wherein we can keep updating it, and so on and so forth. So then with these kinds of emissions, we want to run them through air quality models. And what are these air quality models? But once again, just quickly running through the basic math. In order to be able to simulate the atmosphere, we have first the three basic, which is continuity, Navier-Stokes, momentum, and energy equations, solved to give the entire set of fields: pressure, temperature, relative humidity, divergence, etc., winds. And then we look at, the specific species continuity equation, which is shown here, with N being any one of the pollutants. And you have different transport processes, advection, diffusion, etc., which come from the flow field. And then we have the chemistry, emissions, deposition, etc., etc. So then, what we're saying here is that these can get pretty complicated too. The emissions is what I just described, but that the model contains all of these other processes. So with this understanding, we have to make it discretized over space, an Eulerian grid, and we can run it over only a specific domain over India, in which case we need boundary conditions all around, and lateral as well as top, and the emissions are the bottom boundary condition. And then, we also discretize it in time, in that we're basically saying that we don't solve everything all at once, but we sequentially solve transport, chemistry, emissions, and other processes. So with this kind of background, if we got a chemical transport model, and there are many that have been developed by groups of people, WRF Chem is one that has chemistry and metrology and so on. GeoSchem is another one. Then you have WRF CMAC, which is US EPA's basic model, and there are several in Europe and so on. So if we picked up one of these fairly complicated models and made simulations, will we get the right answer? So the answer is a resounding no. We, will not get the right answer. And in fact, most models are underestimating air pollution levels simulated over India by factors of 2 to 5 or 3 to 5. So there's a lot we have to do to, in a sense, optimize the model. And one of them, of course, was emissions. We've talked about it. But then one needs to tune the dust transport and map it correctly to the boundary conditions. Most of us know, of course, that the size of particles or particle size distribution will determine whether they are transported in the atmosphere, and when they fall out of the atmosphere, and when they can be ingested in the lung, and so on. So this kind of mapping has to be done correctly. And of course, what's written here is that air pollution, the particles themselves contain black carbon or soot organic carbon, and what's shown as mineral matter or MM, which is nothing but ash, whether it's coming from coal fly ash or whether it's coming from, different kinds of combustion processes. And then we have sulfur dioxides, nitrogen oxides, ammonia, volatile organics, which all also react in the atmosphere to form sulfates, nitrates, ammonium associating with them, and what is called secondary organic carbon. And we recognize, of course, that organic carbon has hydrogen, oxygen, etc. So we need to know what kind of enhancement ratio is needed to account for the particulate matter. And there are ways of arriving at this from a combination of ground-based measurements, satellite measurements, and models, which is what is shown for our region here. And then after doing that, we could run a model and then come up with model evaluation. And this is being shown for WRF-Chem, run in my group by Kaushik, Mudchuru, and Arushi Sharma. And we do a set of evaluations. Again, satellite detection, you can see what is called aerosol optical depth, or the extinction of radiation by particles is shown over here. And where you have reds, you have high column aerosol, all of the endogennetic plane, different satellite sensors, MODIS, MISR, etc., etc. And then also ground-based measurements. We're all aware that the pollution control boards and now there's an integrated website where we can download this data. What is being shown here, Arushi has plotted about our model at the background and about 70 to 80 such stations, but this is annual mean. So one of the things I'd like to highlight, if you look at the yellow bar, is the normalized mean bias of what's called PM 2.5, or particulate mass smaller than 2.5 microns. We've been able to reduce the model deficiency to within 10%, minus 0.1 as the normalized mean bias, which is a huge achievement. Because as I said, we would start with something like factor of 3 to 5 lower. After tuning all of these things, we get an annual mean and across spatially bounded at 10%. But we can't congratulate ourselves. We're looking at seasonal differences, underestimations, maybe 25, 30%, as the purple and the green bars show. The other thing that's being shown here in these little plots is these black carbon, organic carbon, sulfate, nitrate, ammonium. We have to get these data from as many stations as we can and evaluate the model. And that's at the surface. We also have aircraft campaigns. This is an aircraft campaign which was conducted by Ministry of Earth Science in collaboration with a UK team. And what is shown here is the flight path and the difference between the model and the measurement at every grid, wherever the height was at that location. And what we're happy to see is a lot of yellows, and whites, so not too much deviation between the model and the measurement. But wherever we see blues, we are seeing underestimation, and this is 10 microgram per meter cubed, which could be a fairly large underestimation given that this is at a high altitude. So the total concentration will probably never be greater than 15 or 20. So we do have evaluation at all these different levels. So then, running some scenarios through the model. These were the earlier discussed sort of scenarios. If we are doing whatever's promulgated now, where will we reach in 2050? And if we really put our minds to it, how much of pollution or emissions can we reduce? And what is being shown here is particulate mass emissions. So it really needs very, very ambitious, sorts of policies. 100% shift from biomass cooking. We have to provide clean and affordable energy to all our citizens. We have to stop the stubble burning problem. And we have a very, very high level of shift from coal. So this scenario here, S3, has like a 75-80% shift away from coal into renewables. And so with these kinds of things, what understanding does it give us? So far, air pollution mitigation and implementation of controls, we keep hearing power plant, industry, transport, odd even policy, some amount of focus on waste burning has come in. But surprise number one. Okay, one thing maybe just to set the record straight is that our human emissions are contributing, and we can see green, blue in most parts of the country. So we say that about 65 to 80% of our pollution is what we are emitting in most parts of the country. The western part is affected by dust coming in from the Arabian side. So there have been various studies, and there's been a lot of discussion about, is it really dust which is causing the air pollution in India, and so on and so forth. And indeed, that is not the case. Then, which is our largest source? So our largest source of ambient pollution in the atmosphere outside that we're breathing is emitted from residential biomass cooking, 24% as shown here. So that's a big surprise. And then if we look at, isolating the sources, and I'm calling it non-formal sectors, residential biomass, open burning of agricultural residues, fired brick production. Of course, I'm pointing out here that this scale is 50%. Here it's 35%, here 6%. So the scales are different just to make it visible. But really, residential biomass is our biggest contributor to outdoor ambient air pollution. If we look at industrial and power plant coal, these you can see, of course, with the industrial coal and the power plants, they're located at the locations in a big way. And the central Indian as well as eastern Indian belt are strongly affected by it. Distributed diesel is tractors and pumps in the agricultural sector, diesel generator sets. So there's sort of an agricultural, but again, let's notice this is only 6% at the top of the scale. And transport, one of the problems with these models is that they are coarse grid. We are not resolving what is the concentration on the roadway. We're resolving the concentration at 25 by 25, or in this particular case, 50 by 50, roughly kilometer level. So on that level, the transport emissions are contributing about 5, 6, 7%. And of course, this study was criticized for that because there is a general feeling in the community of advocacy and control that transport has to be addressed. But there are other statistical studies which have also shown, when we did odd even policy in Delhi and so on, transport contributed between 10 and 15% of improvement, but not anymore. So with that in mind, we're basically, the main takeaway is we need an additional focus on non-formal sectors to really start being able to bring down pollution. So with that idea, we looked at, what's happening in the different states. Delhi is our capital. It's also our air pollution capital. And what we find is that this S3, the very ambitious, we've not tried it but really need to get there scenario, is the only one where the yellow line, which is the National Ambient Air Quality Standard of 40 microgram per meter cubed of PM 2.5, we're in violation in every state except 5 or 6 at the moment. We cannot bring down pollution that much, even by 2030, unless we do something very significant. And if we are able to do that, then all but the top maybe 6 or 7 states in 2050 can come down below the air quality standard. But the sort of discouraging thing is the states where pollution is very high is also where the population is high. So people are getting exposed to the pollution. Another idea was, to look at what is the contribution together of all of these sort of non-formal sources. We call them carbonaceous aerosol sources because they emit black carbon and organic carbon. This is a different model run in my group, 2 sets of simulations here. And what we find, of course, is annual mean looks like this, very similar to another model. October, November is much more polluted, particularly in North India, December, January, February as well. So wintertime pollution is much more than annual mean. And then what is the contribution of the non-formal sources? 60 to 80% in northern India. We really need to control residential, give clean residential energy, affordable residential energy to our citizens, and look at, how to control waste burning, how to control dirty combustion in brick kilns, how to control agricultural stubble burning, and so on. So it's not no silver bullet, multiple things that we have to do. And the rest of India, Peninsula and rest of India also has an, not insignificant or fairly dominant contribution from these non-formal sources. So then question number 2, we are doing city action plans for 200 cities under the National Clean Air Plan. Is this the right scale? Do we need to be looking at any other scale? And this was done collaboratively, again, with our emissions. In all these studies, it is our Smog India emissions. Some of them we've run the simulations ourselves. Some of them, the simulations are run by colleagues in a bigger group. And here we are asking the question, suppose we divide North India brown, Indo-Gangetic Plain green. Sorry, there's not much of a contrast, but Western India is purple, Central India is pink, and Southern India is gray, and Northeastern states in yellow. Then suppose we run simulations turning off each individual region. Where is the pollution the most? So, and which the emissions from which region, are they affecting other regions? Can we look at this as a local problem? And so this is sort of where the title of the talk came from. Yes, the Indo-Gangetic Plain is the most polluted and also has the largest population, as we see from this plot. But, if we look at where is the pollution coming from? So Northern India, each region, like Northern India, orange, Indo-Gangetic Plain, second bar green, third bar is Eastern India, yellow, fourth bar Western India, the purple. So each region emissions are the largest influence on its own air pollution. That is clear. But the green appears everywhere. So the largest exporter of air pollution because of metrology and transport are the emissions that lie in the Indo-Gangetic Plain, all the way down to South India. Even 15% or 10 or 15% of South India air pollution comes from the Indo-Gangetic Plain. We have metrology that essentially is a flow from west to east past the Indo-Gangetic Plain, which turns around in the Bay of Bengal and brings that pollution down. So we've seen that metrology in our models. So with this understanding, we find that it is indeed a regional problem. It's not an urban problem. And very quickly, if I would go through some human health impacts, can somebody tell me how many minutes? Because I might skip some slides accordingly.
Yeah, another maybe 10 minutes.
Okay, good.
Yeah.
So I know what to skip now. So very quickly, we have this idea of integrated exposure response curves. And what that is saying is, for these diseases like cardiovascular disease, ischemic heart disease, stroke, lung diseases, lower respiratory disease, if I have exposure of a population, PM 2.5 x-axis at 25, 50, 75, 100, 125 microgram per meter cubed annually, how much am I increasing the relative risk? RR on the y-axis. And where are the data for these fits coming from? At the lower end, the data are coming from developed countries where they have managed to control their air pollution to below, definitely in most locations, below their standard is 12.5, while ours is 40. WHO recommends, 10 microgram per meter cubed. So these data come from longitudinal studies, 10, 20, 30 years of populations in developed countries. As we go to higher exposures, as we call them, we are talking about what are called cross-sectional cohort studies, exposed versus non-exposed, to air pollution, to biomass smoke, and then, of course, at the top end of the distribution, it comes from tobacco smoking. So, and these are data that come from India as well, that, every year, Global Burden of Disease refits these curves with all the new data available and puts it out for the community to use. So with those air quality simulations we had made, if they are put into this kind of a model and you calculate millions of, they call it deaths, but let us say premature excess mortality, people who should not have died dying too early, then, this is what it was in 2015, and every time we do a scenario, yes, when you cut the air pollution, the mortality falls for 2030 and 2050. But what is a little bit discouraging is if you look at the last bar and the big black dot, it is higher than the top of the bar in 2015. So even if we cut air pollution hugely, the aging and increasing population effect makes the mortality amounts in actual amounts, millions, increase by 2050. So, we really need to step up our ambition. This is showing the spatial distribution of mortality. It resembles the kind of, thing that we said earlier, which is, once again, that IGP contributes almost 50% of the air pollution related premature excess mortality in India. Some of it within IGP, the brown, and a lot of it outside IGP as well. Like it's something like 4/5 within the IGP and like 1/5 outside the IGP. So once again, that it is a regional problem, not an urban problem. And then the final question, who is getting affected? If we read the media, we think it is only NCR and it is only the Delhi citizens who need to be protected from air pollution. So this is also a collaborative study in which I was involved, where essentially the new thing we did here was to take satellite sensor data, visible and infrared radiometer, and based on the night light sensing, the regions of higher light intensity are called urban, while lower light intensity are called rural. And this is at a 5-kilometer grid, which is very, very good data in terms of getting to be able to distribute the population correctly. And then we overlay that on the concentrations, and it says satellite derived because the model and satellite are used together. And the takeaway is that non-urban or rural citizens of this country are experiencing about 70% of the mortality from exposure to air pollution. So this is, a very clear, it is not an urban problem. And, once again, what's being shown here is orange curve, which is numbers of people exposed at various levels, 50, 75, 100, etc., microgram per meter cubed. The non-urban population is much more that's getting exposed at all these levels. There's a crossover of the green curve, and that is your really polluted cities. So, 150 and larger, that is where you'd have Delhi, you'd have some of the other cities in the Indo-Gangetic Plain, I believe Kanpur, others are all on that list. And so where, and that's what is getting the press, but we don't have a rural measurement network. We don't have any idea of what's happening to the rest of our citizens. So I'm going to skip this section, which is climate change worsens air quality, except to say that we know that what it's doing is that it's acting through changes in meteorology and chemistry. And as far as meteorology goes, it is lowering the planetary boundary layer because of certain radiative feedbacks happening from particles as well as gases. And so we would expect pollution, if we were emitting at a particular level, to have, as you're pressing it closer to the ground, the concentrations increase. And there are a bunch of different chemistry effects, which I won't go into. So maybe we can skip this and basically come to interventions and solutions, which is where engineers want to be. Other countries, most of them started in the 1950s, and by the mid-1970s already had an operational air quality management system. We did enact our Air Act in 1981. So then the question over here is, we seem to have really fallen behind after that. And we are now enhancing our measurement network under the National Clean Air Plan. But what is missing is an integration and public availability of that data, because just measurements will tell us what the level is. It will not tell us where the pollution came from, therefore what to control. And therefore, this entire system of emissions models, which we've talked about, atmospheric models, which we've talked about, receptor models we've not talked about, and both of them can use a large set of emissions to get better and better confidence in where the sources, what the sources are, and then go back to regulation and implementation, wherein every time you regulate and implement, and we need implementation trackers, and not just at the city scale, but also at the, definitely at the state and district scales, that can feed back into changes in the emission models. And then, we can stay in the cycle until it improves. What we're really saying here is emission inventories, which are those emission models, are important tools. I think it's not that relevant over here. And finally, the role of engineering institutions. So, we definitely need to teach. That's one part of it, but we need to do very focused courses on modeling and so on. So this idea of, these models, it has not become a regular part of curricula, these models are run routinely by regulation agencies in other countries, while groups of scientists keep developing and tweaking them. Here we have maybe 5 groups in India that run these models, and that's it, you know. So we really need to scale this up. And then there's lots of engineering and business opportunity, data analytics platforms, scenario tools, web-based tools, and so on, which can allow state, city governments, etc., to make quick decisions, and implementation trackers. Merely because we say we're going to do something, we don't know whether it's done. And so there's, definitely scope for academic institution partnerships with different types of OEMs, HPC ones, software ones, consulting ones, etc., to maybe develop commercial services. And then once these are, well established, then we have industrial clients, municipal governments, other pollution control boards, etc., and citizen and advocacy groups driving the whole thing, demanding that we have this information available. So I will stop here. This is just a summary. Thank you for your time, and back to you, Suresh.
Thanks, Chandra. I see one question in the chat box.
Let's go to the chat box, please. Should I stop sharing now, Suresh?
Yeah, you could stop sharing.
Okay.
Yeah.
All right. Yeah. All right.
Prof has a question. Probably you could.
Yeah. I can read it now.
Yeah.
It has been suggested that waste biomass from agricultural operations should be used for production of ethanol. To what extent will that contribute to pollution? Okay. So, waste biomass from agricultural operations, being able to use it productively is a very good idea, and is a definitely something that we want to do. Ethanol is one thing. Just densifying the biomass and being able to use it in boilers, industrial boilers. I believe we have a colleague who's interested, and others are interested in using it in walling materials, along with binders and polymers. So, that seems to be one thing engineers can do. But the other perspective is, why are agriculturists burning the fields? Over there, that seems to be an understanding that can we sharing the screen? Okay, thank you. Over there seems to be, a slight understanding that it seems to be more a political type of problem rather than other things, which is that the northern states are producing paddy because of, subsidized water, subsidized electricity. That is also leading to pumping of water out of the water table. And then there is not enough of time between the paddy harvest and the wheat sowing, which is really leading to a large amount of stubble burning in North India. So, I mean, we definitely need to have engineers, companies, industries, etc. But I think we need to find a way to communicate this together in a single voice, and get the political will to, change it as well. And yes, if we are able to compensate farmers. We have a minimum support price for grains. Why not a minimum support price for the residue, which should be seen as resource rather than a waste, if we're able to do that, there could be a transformation in the whole thing. So thank you, Professor Grover. That's, a very interesting question.
Chandra, I have a couple of questions.
Yeah.
When for your atmospheric pollution models that you solve, how easy is it to specify the boundary conditions when you're solving it for the Indian region? I mean, there was recently a concern that dust storms originating in the Middle East were causing haze in
Mumbai.
Yeah.
I'm sorry, that was such a, I'm sorry, that was not a suggestion that could be defensible. So yes, I mean, we do take boundary conditions from from what is called a global model. So the way we run our simulations is there's a biggish box which covers all of India, but you could always have smaller boxes within that, which is called nesting, and come to finer and finer scales and have a box over Mumbai at 3 kilometer or something like that, rather than 25 kilometer all over India. And yet, yes, you have, and our boundary conditions do include the transport of Arabian dust. So it's not as if it's not included in the models. It is 100% there, and it is varying with the strength of the wind, with whether or not there is a threshold velocity for the dust to get kicked up. There is a size distribution of the dust, so whether or not it settles down quickly, all that is there in the model. So that was not, and those days when we got the newspapers saying it's dust storms were very still days. If it's a dust storm, why am I not feeling the wind? So I was a little bit upset to see the papers in those days suggesting that it is dust. We need to really understand ourselves a little bit better. Yeah.
Right. Yeah. Another question. So you're saying that the non-formal sector is a major worry.
Yes.
But then that becomes very difficult to tackle because it's so distributed, right? So
yes, it is distributed. We have right now the Ujjwala program and Saubhagya program, which are supposed to lead to transformation of cooking to LPG and electricity rather than a lot of the kerosene use and so on and so forth. And they are on paper have very good targets and so on, but what we understand from groups who are looking at the data is that an initial connection is given out, but the affordability is so poor that refills are not taken. So as long as people are outside of the cash economy, and so there's always a pressing health problem, a pressing house roof repair problem, some other problem for which the money has to be used before you can buy your next cylinder.
Thank you very much.
There's one from Professor Vasudeva Rao. Is there any correlation of average ambient temperature in different regions on the air quality index? So interesting question there. So I think there's like two things, which is with temperature, there is a way in which atmospheric scientists understand what is called the temperature lapse rate. It's not it's temperature, but also the temperature vertical profile in the atmosphere, and depending on what that vertical profile is, you can have a very stable or a very unstable atmosphere. I mean, basically it's your teapot thing. Is the bottom hot and the top cold? Then you'll have a lot of circulation. Is the bottom cold and the top hot? Then you will have no circulation, right? And in that case, there's a lot of subsidence, or the air pollution comes close to the ground. So what we definitely need to correlate is what is the temperature profile with air quality. And there's also the concept of using it to calculate a boundary layer height, and so we can correlate that. But again, what we're finding, and there's also an observational paper which just got published in Journal of Geophysical Research from our 22 institution network, which is saying that which is showing that it's not meteorology, it is the emissions that are correlating with the levels of air pollution. So, this is something, and, when I said we have 11 stations from Srinagar to Mysuru, Bikaner to Jorhat, and 2 years of very, very intensive sampling, which is the kind of measurements which even our regulatory people are not making and not putting out, I think this data set is telling us that meteorology has some effects, yes, but the emissions have much stronger correlation. So thank you, Dr. Rao.
Thanks, Chandra. I don't think I see any more questions.
Suresh, may I ask one question? Roy here.
Absolutely.
Yeah. I was just going through your full presentation. This because of maybe this time constraint, your slides were too heavy to go through really during the time given. So for our own benefit, can you just give us 2 recommendations, which is really a contribution of your model for the national interest?
Thank you, Dr. Saswati Roy. I would condense it to 2 things. One is, what is the scale of intervention that we require? Right now, the National Clean Air Plan is looking at city scale. We definitely need to go to state district scale. Along with the city scale, we perhaps need to do this more urgently than city scale. That's recommendation number 1. The scale of intervention to address our air pollution problem has to not be limited to urban. The second one, of course, is that at least, we have reasonable evidence now that looking at emission control in industry, thermal power, and transport, which is where the traditional focus has been, is probably going to cut less than 40% of our air pollution. We really need to focus on the non-formal sectors, and there I think it's in our interest, with what we call sustainable development goals, which have been adopted by India, clean and affordable energy being a major one, improving health being another major one, so avoiding air pollution health impacts. So non-formal sector interventions need to be prioritized very urgently. So these are sort of 2 basic takeaways, Dr. Roy.
Thank you. Yeah, over to Suresh.
Thank you. I think we'll have to bring the session to a close because the time is getting on. I will thanks Chandra for that talk and for answering all the questions. I will now request Professor Shashwati Roy to propose a vote of thanks, and I request all the fellows to continue to keep logged in, because we are going to follow this with the annual general body meeting of the Mumbai chapter. Shashwati, to you.
Yeah, thank you, Professor Suresh, for continuing this session so nicely. And I'm sorry to the audience for our slight delay due to this technical glitch. And sincere thanks to Professor Chandra, because I was just going through that how much data and how much analytical things are in it to come up to this, maybe very few recommendations, but they have to be so strong that nationally it has to be accepted. So my sincere regards to all our team members. And additional thanks to our audience for being with us patiently to watch and be with us. Additional thanks also to our INAE colleagues. Because of their help only we are able to continue all these efforts. So with this, I again thank Chandra and her team, and over to Suresh, because now we have to go for our AGM, and I will request all our colleagues, Mumbai colleagues, to be with us. So I send it to Suresh. Thank you.
So thank you, Dr. Roy. Thank you, Suresh. And thank you to the audience for your interest.
Yeah.
It's been a great pleasure.